Welcome to the next lecture. So in this lecture we will see some example questions on per unit system. Now coming to this example, a single line diagram of power system is shown below. Draw the impedance diagram by considering transmission line 1 rating as base. Calculate the driving point impedance of bus 3 and bus 4. That means we need to calculate what is the driving point impedance of this bus and this bus. Okay, but he has clearly mentioned what is the element you have to take the base. That means what is the new base here. So new base is the transmission line 1 rating is the new base. Okay, what is the transmission line 1 rating here? Let's see, transmission line 1, it's clearly mentioned that it's a 140 kV 200 MVA. Okay, so here it is 140 kV and 200 MVA. Clear? Now this is the new base for complete system. Okay, so we already done the calculations. When you are defining the new MVA base for a complete system, the new MVA base will be remain same, but the voltage base will change based on the transformers. So in this circuit 140 kV is the new KVB base. So for transformer high voltage side, KVB new is what? 140 kV. For this transformer also KVB new is what? 140 kV. For this transformer also in this path KVB new is 140 kV. Okay, but when you shift to the other side, the KVB new will change. First we will try to calculate that. So before going for calculation, I will write the KVB old for every element here. Okay, clear? So the KVB old for generator 1 is 11 kV. We already discussed. The KVB old means what? Rating of the machine. So what is the KVB old for generator 1? 11 kV. Clear? Now what about for generator 2 25 kV? That is a KVB old. KVB old is 25 kV here. Now coming to transformer 1, what is the low voltage side KVB old and high voltage side KVB old? That we need to find out. But before that, if you really notice, transformer 1 is clearly mentioned. It is a combination of 3 single phase transformers of each rating of 6 kV by 100 kV x equal to 10%. That means if 3 single phase transformers combine to form a 3 phase transformer, its per unit reactance will change or not change. Its per unit reactance will not change, but what will change? MVA rating will change and voltage rating will change based on the connection. Now clearly speaking, 6 kV is the LV side voltage and 100 kV is the what? HV side voltage. By default this is a phase voltage and this is a phase voltage, but is clearly mentioned it is a star delta transformer. When you are writing the voltage rating of a 3 phase transformer, you must give always line voltage rating. Okay, so 6 kV is the phase voltage on the primary, but primary is star connection. So what is the line voltage? Root 3 times the 6 kV. So I will write here, this is 6 root 3 by secondary is delta. Phase voltage and line voltage are same. 100 kV is the phase voltage of a single phase transformer. So if I convert that into what? 3 phase transformer by using 3 single phase transformers, the line voltage rating also 100 kV. Why? Because secondary side is what? A delta connection. So 6 root 3 and what? 100 kV here. 6 root 3 kV is the primary voltage and 100 kV is the secondary voltage. That means the primary side KVB old is 6 root 3, secondary side KVB old is what? 100 root 3. That's fine. Now coming to transformer 2. Transformer 2 is what? 20 kV by 120 kV 150 MVA x equal to 10%. But careful sir, for a transformer 2, tell me, is it a combination of 3 single phase transformers? That is not mentioned. That means by default it is a 3 phase transformer. If it is really a combination of 3 single phase transformers, definitely it is mentioned in the problem. Otherwise it is a by default 3 phase transformer. 20 kV by 120 kV. 20 kV on which side? LV side. This side is 20 kV. Don't think that this side 20 kV. No, practically it's not correct. Let's see here 140 kV line. So that means the voltage here on the high voltage side is close to 140 kV. If you write 20 here, that is blunder. So it's a common sense. He will not tell you that upside is 20 or downside is 20. You need to apply the common sense here. Anyway, the simple common sense is here. This is 20 kV on the LV side and on the HV side is what now? 120 kV. Fine. So for this transformer KVB old on HV side is 120 kV, LV side is 20 kV. Okay, these are line voltages or phase voltages? Yes, by default for a 3-phase transformers, line voltage ratings only given. Okay, clear. Now generator 2 done, transmission line is done. Now coming to transformer 3. Transformer 3, 132 kV by 33 kV. Now again you have to apply the common sense. Tell me, this side is 33 kV or this side is 33 kV? Better to say this side is 33 kV. And this side is 132 kV. 132 kV is close to 140, but not 33 kV. That's why, let's say, so on the top side I am writing this is 132 kV by 33 kV. Okay, clear. That's for transformer 3. Now this is our transformer 2. Fine. Now finally motor 1 and motor 2. Motor 1, what is a KVB? Old is nothing but 30 kV, and motor 2 also what? 30 kV combinedly. Clear? Now we need to see what is the KVB new and MVAB new. Okay. Now before that, for complete system, what is the MVAB new? Consider the transmission line rating as base. That is the question. Correct or not? Transmission line rating is base, and you need to draw the impedance diagram. That means for a complete system, what is the MVAB new? For a complete system, MVAB new, I will write here. For a complete system, the MVAB new for a complete system is 200. But KVB new, you need to think carefully, depending on what? The network connection. Because at every transformer, you have to shift KVB new from one side to another side. Okay, clear? Now, so let's have a look. What is the KVB new for transmission line? 140 kV only. Why 140 kV? Very simple. Okay, he has mentioned transmission line only base. That's why KVB new for transmission line is 140 kV. Tell me, what about for this side? KVB new, same 140 kV. Why? There is no transformer here up to here. Here only transformer is there. That's why here also 140 kV. Now tell me, what about here, this side? This side again 140 kV. This side again 140 kV. I am writing here 140 kV. On HV side 140 kV. But tell me, what about on LV side? We have just written HV side of what? Transformer 1, transformer 2 and transformer 3. That is same like what? Transmission line. Okay. Now, whenever you shift that KVB new to LV side, that means this side, how much it will become? So, there is a transformation ratio 120 by 20. That means if I give 120 kV, I will get 20 kV here. So, but indirectly what I given here, KVB new 140 kV is given. How much is this side? So, how to calculate that? 140 you given, and transformation ratio is what? 120 to 20. If I give 120, I will get 20, but I given 140, that means 20 by 120. Okay. If I calculate this, we get 23.33 kV. 23.33 kV is the KVB new for what? Transformer LV side and what? Generator 2. Now similarly, what about the KVB new in this circuit? Again sir, what is the KVB new you are given here? 140 kV. So you have to shift it to what? This side. Okay, you have to shift it to this side. So how? Again same, 140 multiplied with, so it is shifting from where to where? 100 to 6 root 3. So you just multiply with 6 root 3 and divide with what? 100. So if I solve this, we get 14.55 kV approximately. So KVB new on the high voltage side of the transformer 1 is 140 kV. But KVB new on the low voltage side of the transformer is what? 14.55 kV. So similarly KVB new for generator also 14.55 kV. Now what left? Now this circuit is left. For this circuit, what is the KVB new? That means for motor 1, motor 2 and transformer LV side, what is the KVB new we need to calculate. So how to calculate? Again you have to shift the KVB new from HV to what? LV using line to line transformation ratio. So 140 you given here, then you multiply with 33 and divide with what? 132. So that is what? The line to line transformation ratio. If I solve this, we get 35 kV. 35 kV is the KVB new on LV side of the transformer 3 and for motor 1 and motor 2. So we are evaluated the KVB new everywhere, and also we are written the KVB old everywhere, and you know the MVAB old and MVAB new for every element, and you know the Z per unit old for every element. Now we need to calculate the Z per unit new by using simple formula. Now we will start from generator 1. For generator 1, if you look, what is the KVB old? Its rating. What is the rating? 11 kV. It's already written here. 11 kV is the KVB old for generator 1. What is the KVB new? 14.55 kV. We are already calculated. What is the MVAB old? 100. What is the MVAB new for complete system? 200 MVA. Okay. So that's why. So I will directly apply the formula. But what is given here? Not the impedances are. Reactances in per unit is given. Okay. Even if the impedances is given or reactances is given, the formula will not change. X per unit new equal to X per unit old multiplied with KVB old by KVB new whole square multiply with MVAB new by MVAB old. I am directly substituting, sir. So I am not writing the formula also, directly substituting, don't confuse. So X per unit new, this is the X per unit new of a generator directly. Okay. So X per unit old is what? 10% means 10 by 100, 0.1 per unit. 0.1 per unit multiply with KVB old by KVB new. KVB old is this red one, 11. KVB new 14.55. So 11 by 14.55 whole square multiply with MVAB new is 200. MVAB old is what? 100. 200 by 100. So if I solve this, we get 0.114 per unit. That is the new per unit reactance of generator 1 by considering transmission line rating as base. Now coming to transformer 1, we are just moving like this. Okay. So for transformer 1, again same story. If you want to calculate the X per unit new from the primary side, or if you want to calculate the X per unit new on the secondary side, but the values will be remain same. That means X per unit new, if you evaluated using primary side parameter or secondary side parameters, the values will not change. Okay. Now I am directly writing for transformer 1, sir. X per unit new equal to X per unit old. For transformer 1, actually transformer 1 is a combination of 3 single phase transformer. And single phase transformer rating is given 6 kV, 100 kV, and single phase transformer X equal to 10%. What is the 3 phase transformer X? 10% only, that will not change. We have seen one problem clearly. If you convert 3 single phase transformer to form a 3 phase transformer, irrespective of its connection, star star, star delta, delta star, delta delta, the per unit reactance will remain same. That means per unit reactance of single phase and per unit reactance of 3 phase is remain same, because by default per unit reactance or per unit impedance are per phase quantities. Okay. So that's why, so 10% only. X per unit old is 10%, means 0.1. What is a KVB new and KVB old? So KVB new for transformer LV side we are evaluated 14.55. So what is the KVB old on transformer LV side? 6 root 3. It is not 6. Why? Because so 3 single phase transformer converted to form what? Star delta transformer. Star means line voltage is what? Root 3 times this phase voltage. If the single phase transformer rating is given, means phase voltage is given, sir, not line voltage. I am converting these 3 single phase transformer to form what? A star delta transformer. Star line voltage is what? 6 root 3. Okay. So 6 root 3 I need to take here. So KVB old is 6 root 3. KVB new is 14.55 whole square. MVAB new is 200 and MVAB old. MVAB old is what now? So actually this is given 25 MVA. One single phase transformer MVA rating is 25 MVA. Okay, clear? I forgot to mention this. Please update in the question. Yeah, one single phase transformer MVA rating is 25 MVA. So 3 single phase transformers are forming a 3 phase transformer. What is the MVA rating? Is it 25 MVA? No, 3 times 25 MVA, that becomes 75 MVA. So that's why, so 200 by 75 whole square. If I solve this, we get 0.136 per unit, sir. Square will not be there, okay? 200 by 75, that's it. 0.136 per unit is the new per unit reactance of transformer 1. Now, let's see, we will solve for transformer 2 and generator 2. Later, we will move on this section, okay? Coming to transformer 2. Transformer 2 now, okay, fine. Transformer 2 is what? A 20 kV by 120 kV, 150 MVA, x equal to 10%. That means x per unit old is 0.1 for transformer 2. Per unit old 0.1 multiplied with what is the KVB new? Now we are on what? HV side. If you want, take LV side or HV side, both are same. Okay. Now let's take HV side, nothing wrong. HV side KVB old is 120. KVB new is what? 140. Okay, just like a transmission line 1, correct or not? Because the transmission line is directly connected here, right? 140 kV is the KVB new, 120 kV is the KVB old. So 120 KVB old, 140 KVB new, whole square. MVAB new and MVAB old. MVAB new anyway 200 and MVAB old, let's see what is the transformer 2. MVA rating 150, so 200 by 150. If I solve this, we get 0.9098 per unit. That is the new per unit reactance of transformer 2. Now after transformer 2, who's next? If you go like this, generator 2. Now coming to generator 2. Generator 2. Tell me, for generator 2, what is the KVB new and KVB old? KVB old is 25 kV. KVB new is what? We are evaluated, sir. So we are shifted 142 low voltage side. 142 low voltage side, if I shift, then I got 23.33. So X per unit new of a generator 2 is X per unit old of generator 2 15%. So 0.15 into KVB old is 25, KVB new is 23.33, 25 by 23.33 whole square into MVAB new for a complete system 200, MVAB old of a generator, check, 80. So if I solve this, we get 0.43 per unit approximately. Now after generator 2, now coming to transmission line, because we have finished G1, T1, G2, T2. Now what next? Transmission line. For a transmission line, what is the KVB new? 140. MVAB new? 200. Old and new are same. But what is given for transmission line? Check transmission line data here. Transmission line actual reactance is given. So you need to calculate the per unit reactance using Z base new. But Z base new, Z base old are same. Why? Because in the problem he has clearly mentioned, take the transmission line rating as base. So that's why X actual is 32, but we require X per unit for transmission line. So directly I am writing X per unit for transmission line is X actual is 32 by Z base. Z base means what? KVB square by MVAB. KVB square by MVAB is the Z base. What is KVB? 140. MVAB 200. 140 square by 200. So if I solve this, we get 0.326 per unit approximately. That's about for transmission line. After transmission line, coming to transformer 3. Transformer 3, now we are on LV side. Now tell me what is HV side. HV side, what is the KVB new? 140, KVB old 132. Okay. So transformer 3, yeah, old per unit reactance is 10. So X per unit new equal to old is 10 means 10% means 0.1 per unit. Now multiply with KVB old 132, KVB new 140 whole square, MVAB new 200, MVAB old. MVAB old is what? Transformer 3, what is the rating? 200. Okay, 200, fine. If I solve this, we get 0.89 per unit approximately. Sorry, 0.089. 0.089 per unit is the transformer 3 per unit reactance, new per unit reactance. Okay. Now after that motor 1 and motor 2. Now coming to the motor 1, what is a old per unit reactance of motor 1? Yeah, motor 1 is 20%. So X per unit for motor 1 is equal to 0.2 multiply with KVB old is 30, KVB new we are evaluated as 35. How we are evaluated? By shifting 140 kV to what? LV side by using line to line transformation ratio of transformer. That is what we done here. Check. So we got 35 kV. So KVB old is 30, KVB new is 35, 30 by 35 whole square multiply with MVAB new 200, MVAB old is 100. So 200 by 100. If I solve this, we get 0.293 per unit. That is for motor 1. Now coming to motor 2. What is X per unit new of motor 2? X per unit old. X per unit old of motor 2 is 0.25. Multiply with 30 by 35 square. Multiply with 200 by what is the MVA old? 80. If I solve this, we get 0.459 per unit. That is a new per unit reactance of motor 2. So we are evaluated the new per unit reactances for all the elements by considering transmission line rating as base. Clear? Now we need to draw the impedance diagram. Strictly speaking, it is a reactance diagram only because resistance of all the elements are not given. Shunt branch impedance of transmission lines are not given. No static loads are there. So nothing wrong to say it is a reactance diagram. So we are going to draw the impedance diagram for this. I will start from generator 1. Generator 1 means a voltage source in series with impedance, but anyway reactance term only present here. Okay, let us say this is the bus 1. Clear? So the generator is connected. Now this is what you can say reference. Now after the generator 1, transformer 1. Transformer in per unit form is represented with simple series impedance or series reactance. Just I am drawing reactance here. Okay, so this is transformer 1 connected between 1 and 2. Now at bus 2 there is a transmission line is connected this side, right, and but downside what is connected? A transformer and generator cascade combination is connected, means transformer 2 I am writing like this. Let us say this is bus 3. Now after that generator means a voltage source in series with reactance. That's it. This is what generator 2. So EG1 and EG2. Right. And after the bus 2, let's move on to the right side. There is a bus 4 here. From bus 4, a transformer T2 is connected between 4 and 5 buses. Then after that, 2 motors are connected in parallel. Motor 1 I am showing. This is for motor 1. I can write EM1 here. Now this is for motor 2. I can write EM2 here. So let's write the per unit reactances, sir. Anyway, per unit reactance of generator 1, 0.114 per unit. Let me write here. I will write like this. In the impedance form I will write, because he is asking the driving point impedances. He has not mentioned the reactances. Driving point impedance means J will come definitely. Driving point reactance means that J will not come. Okay, because impedance of reactance is Jx. Reactance means it's a real number. Impedance of reactance means it's a J times something. Okay, careful about this. Anyway, J 0.114 per unit. 0.114 per unit. I am not writing the per unit, sir. By default they are in per unit. Careful. J 0.114. Then after that transformer 1. Okay. Transformer 1 we got 0.136 directly J.136. Then transformer 2, if you go down, transformer 2 we got 0.098. Then generator 2 we got 0.43 per unit, so J 0.43 per unit. Then transmission line we got transmission line 0.326. Then between 4 and 5 we have a transformer 3 for which we got 0.089 per unit. Then motor 1 and motor 2. Motor 1 this, motor 2 is this. Motor 1 we got 0.293 and motor 2 we got 0.459 per unit. Now coming to the last question. After drawing the impedance diagram, we need to calculate the driving point impedance of bus 3 and what? Bus 4. See, bus 3 and bus 4 we need to calculate. Have a look, sir, how to do this. See, that means indirectly you have to calculate by looking into this terminal from reference. This impedance we need to calculate. So, before calculating that, we need to short circuit the voltage sources, right? Okay, if I short circuit here and this voltage source also I am short circuiting, these two also I am short circuiting. Now just check what I get. See, this and this combination in parallel, that overall parallel combination is in series with this. Now that entire combination is in parallel with what? 0.43. Again I am saying, sir, let us see, this is what I will write like this till here, from here to here 1 I am saying. Now from this complete, these two are you parallelly combine, okay, and that is what 2. This section impedance and this section total impedance are in what? Parallel. Now that overall is in series with what? 3. This is the section 3. Now 1, 2, 3 you combined, that overall again in parallel with what? 0.43. Okay, 0.43 is parallel with what? The complete thing which I have written here, complete thing. Okay, so I am writing Z Thevenin at bus 3. Please careful here, Z Thevenin at bus 3. I am directly writing 0.43 is the parallel combination of what? This entire circuit equivalent impedance. So I am writing 0.43 parallelly combined with what? Start from here. 0.098 is series with what? Parallel combination of 1 and 2. Okay, so 0.098 plus you need to parallelly combine 1 and what? 2. Now I am going to write 1 here. Let us see. 1 is what? There are 2 reactances in series. 0.114 plus 0.136. That is at what? 1, section 1. Now coming to section 2. Section 1 and section 2 are in parallel. That is in series with what? 3. The whole thing is in parallel with what? 0.43. That is what I am writing here. 0.43 in parallel with what? Series of 0.098 in parallel with section 1 and what? Section 2. Now section 2, if you start from here, section 2 is what? 0.326. That is in series with what? 0.089. Then after that is in series with what? Parallel combination of these two, means 0.293 parallelly combined with 0.459. So this is section 1 and section 2. Section 1 and section 2 are in parallel, that is in series with what? Section 3. The whole thing is in parallel with 0.43. So if I solve this, I got 0.593 8. If I solve this, I got 0.25. Now if you parallelly combine this, that means 0.25 parallel with 0.5938, then I got 0.176 per unit. Now 0.176 is in series with what? 0.098. So finally we got what? 0.43 parallel with 0.274. So if I solve this, we get 0.167 per unit. But careful sir, this is X Thevenin, not Z Thevenin. So Z Thevenin means what? The J will be coming into picture. At the end you just attach J. Now that is the final driving point impedance of bus 3. Now similarly you need to calculate the driving point impedance of bus 4. So I will tell you how to do that, but you have to do the calculations. So let's see here the driving point impedance of bus 4, how to evaluate that. So bus 4 is here, you have to looking into this terminal. If you looking into this terminal, just check sir, let's say this is section 1, this is section 2, this is section 3, and then after that what? This complete is section 4. So 1 and 2 are in parallel, that is in series with 3. After that 1 reactance you get. Then this side, this 0.089 is in series combination of what? Parallel combined value of 0.293 and 0.459. That means first you parallelly combine this and add with 0.089. Okay, then whatever the resultant you get and whatever the resultant you get here, both are in parallel. So you need to solve for Z Thevenin at bus 4 using the approach what I explained. Now coming to this example, a single line diagram is shown below. Calculate the internal voltage in kV per phase by considering bus 3 voltage is reference. He is clearly mentioned bus 3 voltage. This is bus 1, bus 2 and this is bus 3. Bus 3 voltage reference means 120 kV is our reference. Okay. So better to convert this into what? Per unit form, and finally we give the answer in actual form. You can do it in actual form also. Okay, but because of the transformer presence, the calculation become what? Bit complex. That's why I am doing everything in per unit form, and finally I will calculate the generated voltage in kV. Okay, but you can consider any base. The final answer will not change. Why? The final answer is not in per unit, it is in what? Actual. So that's why the base is up to you. Whatever the base you consider, the per unit values may change, but the final actual value, the final answer will never change. For example, I consider generator rating as base, somebody consider transmission line rating as base, otherwise transformer rating as base. Whatever you consider sir, final answer is actual value, that will not change. Per unit values will change. For your base, whatever the per unit value of EG you got, for my base whatever the per unit value of EG I got, definitely different. Okay, because if you consider the different base and I consider a different base. So that's why finally what my point is, you consider your own base and calculate EG in per unit. Okay, clear? So anyway, how to calculate this? So this is what EG, and that is in series with ZG. Then bus 1. Transformer is represented with simple series impedance. After that transmission line is represented with simple series impedance. Now you know what is the current here. I can calculate the current in what here? Per unit. Once I know the current vector in per unit, I can calculate EG. Okay, ZG, this is ZTF, let's say this is ZTL. Now you know the voltage here, V, that is also in what? Per unit. Okay, so if you know the V, then what is EG sir? EG equal to V plus the voltage drop. What is that? I into ZG plus what? ZTF plus what? ZTL, simple KVL. That's what EG bar. So using this we can calculate. But let's proceed from here. V. So V is the 120 kV here. But we have to convert this into a common base first. To do this analysis, we must convert onto a common base. So base value is not mentioned. That's why what I am doing here is I will consider the generator rating as base. By considering generator rating as base, I will convert the per unit reactance of all the elements onto a common base. If I take generator rating as base, then what? Generator per unit reactance will not change, because kVb old is 11, kVb new also 11. MVAB old is 120, MVAB new also what? 120. So that's why here the per unit reactance of the generator is remain at what? 0.1 per unit. Okay, generator story is over. Now coming to the transformer story. But careful, what is the kVb new in the circuit? I will write here. kVb new up to here, up to the primary of the transformer, 11 kV. And kVb new up to here, because only one transformer, two sections. Now you have to shift 11 kV to this side. We get 132 kV only. Why? Very simple. See, generator rating is the new kVb. New kVb is 11, and it is transformer which is shifting from 11 to what? 132. I given 11, I will get definitely what? 132 kV. Okay, so this is the line voltage base which is 132 kV. This is the line voltage base which is 11 kV. Okay, line voltage base, careful sir. In the generator circuit we get what? Line voltage base, that is what? 11 kV. In the transformer secondary side, line voltage base is 132 kV. Transmission line also 132 kV. Any transformer here? No. That's why what is the kVb new for this? Also what? 132 kV. Okay. Now, so this is done 0.1 per unit. Fine. Coming to the transformer. Transformer, what is the X per unit new? For a transformer, X per unit new is, I will write here, transformer, directly I am substituting sir. X per unit new for a transformer is, X per unit old is 0.1, kVb old is 11, kVb new also 11, check sir, in the low voltage side. Then MVAB new is 120, MVAB old is what? 100. So we get 0.12 per unit. That is for transformer. The who's next in the line? Transmission line. Now coming to the transmission line is the actual impedance is given. So that's why, so that is J10 is given. So that's why what is XTL here? 10 ohms. XTL in per unit form. XTL in per unit form is what now? 10 by Z base. What is Z base? 132 square by 120. I think you understand. Sir, kVb new here is 132 kV. For a complete system, what is the MVAB new? Since I proceeded in this question by taking generator rating as base. So that's why for a complete system, MVAB new is 120. So if I solve this, we get 0.068 per unit. That is a transmission line per unit reactance. Now after the transmission line, coming to the load circuit. Sir, the load is delivering how much complex power? Magnitude of S is 100 MVA. So when it comes to the load, what is the magnitude of S? 100 MVA. Okay, in per unit form, 100 divided with what? 120 per unit. This is the magnitude of S. Power factor is what? Anyway 0.8. That will not change. And what about the voltage, sir? This is what our reference. Correct or not? That's why V bar equal to 120 is the line voltage. Okay, and phase voltage is 120 by root 3, but you don't need to worry sir, because when you are doing in per unit form, line voltage per unit, phase voltage per unit are what? Same in magnitude, and phase angle for phase voltage only 0 degrees sir. Okay, not for line voltage. So V bar, I am writing this 120 by, okay, magnitude of V, better, magnitude of V, the line voltage in per unit. Okay, 120 by, what about the base voltage here? 132, 120 by 132 at an angle what? 0 degree, sorry, magnitude only na. So if I solve this, 0.909 per unit. Clear? But what about the voltage, phase voltage in per unit? V bar in per unit is equal to 0.909 is the line voltage in per unit, phase voltage in per unit also same. Okay, so at an angle 0 degrees, 0.909 at an angle 0 degrees. Now what is this value? 100 by 120 equal to 0.833. This value is 0.833 per unit. So finally we need to evaluate the current here. Clear? So we know that magnitude of S equal to in per unit form sir, magnitude of V into magnitude of I. Let's calculate the magnitude of I from here. Magnitude of I equal to magnitude of S by magnitude of V, that is equal to 0.833 divided with 0.909. If I solve this, we get magnitude of I equal to 0.9166 per unit. That is the magnitude of I. What is I phasor? Magnitude of I at an angle something. What is that angle? Power factor angle you need to consider. But what is the power factor he has given? 0.8 lag. So that means magnitude is 0.9166 at an angle of minus 36.86. I think you understand why we are putting here minus, because it's a lagging power factor, 36.86. Cos inverse of 0.8, 36.86. Now that's about the current. So we got the current now, we got the voltage now, we got the per unit impedances. Now you can substitute in this question, in this equation. Eg equal to V bar. What is V bar? 0.909 at an angle 0 degrees plus the current 0.9166 at an angle minus 36.86 degrees. Clear? That's about the current. Voltage plus current multiply with what? The total impedance. J.1 here, generator. Now transformer J.12, then transmission line. Transmission line is J0.068. So if I solve this, we get Eg equal to 1.088 at an angle 11.19 degrees. That is what? Eg in per unit. Clear? The Eg in per unit we got. Now after calculating Eg in per unit, you must multiply with what? The base voltage. Base voltage where? In the generator circuit. Don't take here the base voltage. This base voltage. What is the base voltage here? 11 kV. That is the line voltage base. What is the phase voltage base? 11 by root 3. So finally the answer is here Eg equal to 1.088 at an angle 11.19 degrees. This is the phase voltage or line voltage? Okay, phase voltage in per unit. Multiply with phase voltage base. What is the phase voltage base? 11 by root 3 kV. Now that is the final answer. Now coming to this question, a star connected load is supplied from a 3-phase balanced supply with line voltage equal to 100 angle 0 degree per unit and line current equal to 100 angle minus 45 degree per unit. Calculate the load impedance in per unit. That's the first question. Second question, calculate the actual and reactive power drawn by the load in per unit. Sir, it is a star connected load supplied from what? 3-phase balanced supply. Okay, system is balanced indirectly. So line voltage given and line current is given. Okay, clear. But first question is load impedance. Sir, load impedance means by default load is per phase quantity. So it might be a star load or delta load. The load impedance is equal to what? V phase by what? I phase. Clear? In actual form or in per unit form, same procedure. Okay, V phase by I phase. But what about V line per unit given? V line per unit is given as 1 at an angle 0 degrees. If that is the case, what about V phase per unit? Shall I say 1 by root 3? No. In per unit form, magnitude of the line voltage, magnitude of the phase voltage are what? Same. So 1 at an angle. Phase voltage lags the line voltage by 30 degrees. So minus 30 degrees. We clearly discussed this. Okay. So that's about phase voltage. What about the phase current and line current relation? Phase current in per unit equal to line current in per unit. So that is 1 at an angle minus 45 degrees per unit. Fine. Okay. Now finally we need to calculate the Z phase. Z phase is V phase by I phase. V phase is 1 at an angle minus 30 degrees and I phase is 1 at an angle minus 45 degrees. So if I calculate this, we get 1 at an angle 15 degrees ohms. So the phase angle is positive, so definitely it is a RL impedance, not RC impedance. 1 at an angle 15 degrees ohms is the load impedance load impedance. ZL means don't think that line impedance, sir. No concept of line impedance here. Z load, okay, is 1 at an angle 15 degrees. Now what is the next question? The active and reactive power drawn by the load. See, to calculate the active and reactive power drawn by the load, so I can calculate the complex power. Complex power is what? In per unit form. V phase into I phase conjugate. Don't write V line I line conjugate, that is blunder. Okay, V phase into I phase conjugate. Don't write 3 here. 3 will not come in per unit system. Be careful about this. What is the V phase? V phase, just now we calculated now, 1 at an angle minus 30 degrees. 1 at an angle minus 30 degrees is the V phase. What is the I phase conjugate? I phase is 1 at an angle 45 degrees. So conjugate means 1 at an angle plus 45 degrees. Clear? So finally what I get now here, 1 at an angle 15 degrees is the complex power. In that, real part is the active power and imaginary part is what? Reactive power. So what is the real part here? 1 cos 15, which is equal to 0.965 per unit. Now imaginary part is what? 1 sin 15, which is equal to 0.258 per unit. That's about the active and reactive power drawn by the load.